I welcome you all to my 35th lecture on digital signal processing. That is UEC 502 for electronics and communication engineering students and electronics and computer engineering students. Today we will discuss two-channel quadrature mirror filter bank. The basic building block in applications of quadrature mirror filters, that is QMFs, is the two-channel QMF bank shown in the following figure. Now look at the block diagram. Here Xn is the input, which is first fed to low pass filter with system function H0Z. And the output of this low pass filter is given to a downsampler, which is going to downsample it by a factor of 2. And the output of downsampler is XA0, capital XA0, as shown on the screen. In the parallel branch, Xn is fed to a high pass filter with system function H1Z, which is also downsampled by a factor of 2, and the output is capital XA1 as shown on the screen. So this unit, this section is called analysis section. Here low pass filter acts as and pre-filtering configuration, that is anti-aliasing filter. Now here in the second part, there is a synthesis section. Now in the first branch of synthesis section, input is capital XS0, which is modified version of capital A0, and XS0 is processed by an upsampler by a factor of 2. That is, XS0 is upsampled by a factor of 2. And the output of upsampler is given to a filter with system function G0Z. And the output of this filter is given to a summing circuit. And here XS1 is upsampled by a factor of 2 here, and the output of upsampler is given to a filter with system function G1Z, and the output of this filter is also fed to the summer as shown here, and the net output is X cap N. Now X cap N is a modified version of Xn. It is not exactly matching Xn, and this section is called synthesis section. Now we will look at the magnitude response of the filters H0Z and H1Z. So we will consider their DTFT. Now these are brick wall filter response. So look at this. This is the response for H0 omega, and from pi by 2 to pi, the response of H1 omega is clear. So H0 omega and H1 omega are symmetrical about pi by 2. Now this figure shows a rough representation of practical magnitude response for the filters H0 omega and H1 omega, but still it is symmetrical about pi by 2. This is a multi-rate digital filter structure that employs 2 decimators in the signal analysis section and 2 interpolators in the signal synthesis section. The low pass and high pass filters in the analysis section have impulse responses H0n and H1n respectively. Similarly, the low pass and high pass filters contained in the synthesis section have impulse responses G0n and G1n respectively. The Fourier transforms of signals at output of 2 decimators are capital X A naught omega is equal to 1 by 2 bracket capital X omega by 2 into H0 omega by 2 plus capital X omega minus 2 pi by 2 into H0 omega minus 2 pi by 2. Mark it as equation A. And similarly, capital XA1 omega is equal to 1 by 2 bracket X omega by 2 into H1 omega by 2 plus X omega minus 2 pi by 2 H1 omega minus 2 pi by 2. Mark it as equation B. So we have DTFT of the signal received here, that is capital XA naught omega and capital A1 omega we have in the frequency domain. Those are represented by A and B, equation A and B. Now capital X S0 omega and capital X S1 omega represent the two inputs to the synthesis section. Look at the block diagram. So look at this input to the synthesis section are capital X S0, capital X S1. Now if X S0 omega and X S1 omega represent the two inputs to synthesis section, the output is simply capital X omega is equal to X S0 2 omega G naught omega plus X S1 2 omega G1 omega. Mark it as equation C. Subsequently, substitute equation A and B in C. So we will have to look at what is equation A. So this is what we have done. So substitute equation A and B in equation C. When it follows that, we will come to this step, but substitute equation A and B in equation C, assuming that XA0 omega is equal to XS0 omega and XA1 omega is equal to XS1 omega. What is the meaning of this? This means we have directly attached the analysis section with the synthesis section. This means capital XA0 is equal to capital S0 and capital XA1 is capital X S1. So we have directly attached the analysis section with synthesis section. Now it follows that capital X omega cap X cap omega capital X cap omega is equal to 1 by 2 bracket H naught omega G naught omega plus H1 omega G1 omega into X omega. This is first term. Plus 1 by 2 H naught omega minus pi G naught omega plus H1 omega minus pi G1 omega bracket closed into X omega minus pi. This is second term. Mark it as equation D. We have considered that the analysis section is connected to the corresponding synthesis section directly, which we have just discussed by this assumption. So at the output of the QMF filter bank, look at this. The output of the two-channel QMF bank is X cap omega, that is in the DTFT domain. So we have equation D with us for analysis. The first term in equation D is the desired signal output from the QMF bank. And the second term in equation D represents the effect of aliasing, which we would like to eliminate. So this is the desired signal output from QMF bank. This is the aliasing, effect of aliasing, which we would like to eliminate. We know that X cap omega is equal to X cap e raised to j omega is equal to X cap Z at Z is equal to e raised to j omega when R is equal to 1. Mark it as equation E. That we know that on the unit circle in Z domain DTFT exists. So from that we can have it in the Z domain also. Therefore, in the Z domain, the equation D can be expressed as, this equation D can be expressed as X cap Z is equal to 1 by 2 X cap Z is equal to 1 by 2 bracket H naught Z at G naught Z plus H1 Z into G1 Z into XZ plus 1 by 2 bracket H naught minus Z G naught Z plus H1 minus Z G1 Z into X minus Z. Mark it as equation J as shown. Now XZ is the Z transform of the input signal. So this gives me opportunity to represent equation J as X cap Z is equal to QZ XZ plus AZ X minus Z. Now QZ and AZ appear as transfer functions. So x cap z is equal to qz into xz plus az into x minus z. Mark it as equation K. But what is qz? Qz is equal to 1 by 2 bracket h naught z g naught z plus h1z g1z. This transfer function just introduced distortion. Now az is 1 by 2 bracket h naught minus z g naught z plus h1 minus z g1z. This transfer function introduced aliasing. So this introduced distortion, this introduced aliasing. So very important. This is mark this as equation L. Now elimination of aliasing. Now this transfer function is introducing aliasing. And next step we will discuss elimination of aliasing. To eliminate aliasing, we require that az must be 0. That is eliminate aliasing by considering az is equal to 0 in equation J and K. In J and K, we will assume az is equal to 0. So that leads to h naught minus z g naught z plus h1 minus z g1z is equal to 0. Mark it as equation M. Now in frequency domain or DTFT domain, this condition becomes h naught omega minus pi g naught omega plus h1 omega minus pi g1 omega is equal to 0. Mark it as equation N. This condition can be simply satisfied by selecting g naught omega and g1 omega as g naught omega is equal to plus h1 omega minus pi and g1 omega is equal to minus h naught omega minus pi. Mark it as equation O. Thus the second term in equation D vanishes. So we have eliminated aliasing. The second term in equation D vanishes and the filter bank is alias free. But this condition need to be fulfilled, that g naught omega is equal to plus h1 omega minus pi and g1 omega is equal to minus h naught omega minus pi in equation O. Let us assume that h naught omega is low pass filter. The magnitude response is like this. Okay, so h1 omega is the mirror image high pass filter and its magnitude response is like this. Both are symmetric about pi by 2. This is mirror image characteristics of the analysis filters. So this is about analysis part, analysis filter part. And you know, here it is clear that if you want to get rid of aliasing, then synthesis filters are also with you in terms of analysis filters. So you will have to fulfill the condition number O, equation number O. Now it is apparent that now we consider that we have a prototype filter H omega with us, low pass filter. We have a low pass filter H omega with us. Low pass filter with system function H omega. So H naught omega is equal to H omega, we consider. So then H1 omega will be equal to H omega minus pi in frequency domain, that is DTFT domain. Now taking its I DTFT, we will get H naught n is equal to Hn and H1 n is equal to minus 1 raised to power n Hn. Mark it as equation R. Now H naught omega and H1 omega have mirror image symmetry about the frequency omega is equal to pi by 2. To be consistent with constraint in equation O, we select the low pass filter G naught omega as G naught omega is equal to H omega, mark it as equation U1, and the high pass filter G1 omega as G1 omega is equal to minus H omega minus pi, mark it as equation U2. In time domain, these relations appear as G naught n is equal to Hn and G1 n is equal to minus 1 raised to power n Hn. This is very simple to show. In Z domain, H naught Z is equal to Hz, H1Z is equal to H minus Z, G naught Z is equal to Hz, G1Z is equal to minus H minus Z. So these are the relations pertaining to the elimination of aliasing. Mark these as U3. Mark these as U3. Now condition for perfect reconstruction. Now we want to reconstruct the signal. With Az is equal to 0, we now consider the condition for which the output x cap n of QMF bank is identical to the input xn, except for an arbitrary delay for all possible inputs. Now, for the above analysis, we made an assumption that we have directly attached the analysis bank with the synthesis bank. So we want to reconstruct the signal that is input xn, that reconstruct the signal input xn at output. So x cap n must resemble xn. There can be some delay in output. When this condition is satisfied, the filter bank is called perfect reconstruction QMF bank. That is when x cap n is very approximately equal to xn. Therefore, we require that Qz is equal to 1 by 2 h naught z, g naught z, h1z, g1z is equal to z raised to minus k. So we are considering this because only possible way is to just have delay in the output, and to make the distortions approximately nil. So we consider that Qz, that the transfer function which was which is responsible for distortions, that should only introduce delay. So Qz is equal to 1 by 2 h naught z, g naught z plus h1z, g1z is equal to z raised to minus k. Mark it as equation V1. By making use of equation U3, the condition for perfect reconstruction may be expressed as, these are the this is the U3, and these relation pertaining to the elimination of aliasing. These came when we try to eliminate the aliasing. So this solution is with us in the form of equation U3. We will make use of equation U3 and substitute the value here. The condition for perfect reconstruction may be expressed as 1 by 2 bracket h square z minus h square minus z is equal to z square minus k. Mark it as equation V2 in Z domain. Equivalently, in frequency domain, h square omega minus h square omega minus pi is equal to 2 e raised to minus j omega k. That is in the DTFT domain. Mark it as V3. Therefore, for perfect reconstruction, the frequency response capital H omega of low pass filter in the two channel QMF bank must satisfy the magnitude condition as magnitude h square omega minus h square omega minus pi is equal to C. That is, C is a positive constant, V4. So this is very important. If h omega satisfies the magnitude condition in equation V4 and is designed to have linear phase, then the QMF output x cap n is simply a delayed version of input sequence xn. So I repeat, if h omega satisfies the magnitude condition in V4 and is designed to have linear phase, then QMF output x cap n is simply a delayed version of the input sequence xn under ideal conditions. Now we will discuss case 1, case A. However, the linear phase is not a necessary condition for the perfect reconstruction. This filter bank is said to be magnitude preserving if we consider or permit nonlinearity in phase. In case B, however, if the filter bank is said to be phase preserving, that means we preserve the phase, then we observe magnitude distortion. So these are the two cases A and B. Now we will go for the polyphase form of QMF bank. The two-channel alias-free QMF bank can be realized efficiently by employing polyphase filters. For this purpose, the filters H0Z and H1Z can be expressed as H0Z is equal to P0Z square plus Z inverse P1Z square, marked as equation W1, and H1Z is equal to P0Z square minus Z raised to minus 1 P1Z square, mark it as W2. By using the relations mentioned in equation U3, by using the relationships mentioned through equation U3, we will have a look at U3. So these are the relation pertaining to elimination of aliasing. By using the relations mentioned through equation U3, we obtain the polyphase representation of filters G0 Z and G1 Z as G0 Z is equal to P0 Z square plus Z inverse P1 Z square, mark it as equation W3. At G1 Z is equal to minus bracket P0 Z square minus Z inverse P1 Z square, mark it as equation W4. So this is polyphase realization of QMF bank. This is synthesis section, analysis section, and this is synthesis section. And we have directly attached the analysis section with the synthesis section. That is why we have plotted the boundary that up to this point, this is analysis section. And after this point, this is synthesis section. The output is X cap and input is Xn. Now we can see that this structure looks to be computationally inefficient. Now this is polyphase filter. This is another polyphase filter. This is downsampler. This is upsampler. And this whole structure is polyphase realization of QMF bank. Now we will try to reduce its computational complexity. Instead of this structure, we will prefer this. Why? How? Now, here this is the downsampling unit, and this is a polyphase filter. Here it is the downsampling unit, and this is a polyphase filter in the analysis section. Now, in the previous lectures, we have done first noble identity, by which we have opportunity to swap the position of these two blocks, the downsampling block and this filter, by making appropriate changes in this filter impulse system function. So we can swap the changes, but this change is not direct change, or we cannot directly swap the position of downsampler with this filter. We need to modify it to swap the position. So we will modify it as per the first noble identity. And now downsampler block is here, and after that there is a polyphase filter P0 Z. And here downsampler is here, and now here polyphase filter is here. Now this is analysis section and this is synthesis section. And this is computationally efficient polyphase realization of the QMF bank. And that is only by using the first noble identity, which we have discussed in the previous lectures. The output of both configurations will be same. That is, output is X cap n, and here output is X cap n. Both will be same. But the implementation of this configuration is computationally efficient. So we will prefer this for QMF bank. So this is very important because polyphase, we will use polyphase filters to realize QMF bank. That is, the two-channel alias free QMF bank can be realized efficiently by employing polyphase filters. And we have got the computationally efficient polyphase realization of QMF bank here. So this is very important article. I finish my lecture here today. This is from the book of John G. Prokis on digital signal processing. You can consult SK Mitra also. That is digital signal processing by SK Mitra. I think that's all for the day. Thanks for attending the session on DSP. See you in next lecture.